Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over a third example problem of how to use Dalton's law of partial pressures. In this problem we have two parts. So let's start with the first part, part A. So, excuse me. So we have a typical neon light that contains neon and argon gas mixed together. So we're asked if the total pressure of this mixture is 1.30 kilopascals and the partial pressure of neon is 0.27 kilopascals. What is the partial pressure of argon? So if we know what Dalton's law of partial pressure says, it says that the total pressure of the mixture is equal to the partial pressures of each gas as if it was by itself. So we can use that formula. So the formula is the total pressure. Oops. So the total pressure is equal to the partial pressure of argon plus the partial pressure of neon. And so we're given the total pressure. So the total pressure is 103. So we can put 103 kilopascals, and that's going to be equal, oops, not 103, it's 130. I am dyslexic. Okay, so 1.30, and excuse me, we're given that the partial pressure of neon is 0.27. So we can take the partial pressure of argon, add to that the partial pressure of neon, which is 0.27 kilopascals. And now we have everything filled out. So all we need to do is subtract both the partial pressure of argon, or I'm sorry, neon, from both sides. So when we do that, we end up getting the partial pressure of argon is equal to 1.3 kilopascals minus the 0.27. So 0.27 kilopascals. And then when we subtract, what we get is 1.03 kilopascals for the partial pressure of argon. So now we have to think about sig figs here. So because we're adding and subtracting, or we're subtracting, but with regard to adding and subtracting, the rule is that the number of digits you have, or I should say, the number of sig figs or digits, significant digits you have in your answer is going to be dictated by the decimal places. So your answer should have the same number of decimal places, or as the measure with the least number of decimal places. Or another way to put it, and maybe even a better way to put it, is that your answer should only be as precise as the least precise measurement. So here we have two decimal places. So the last digit is in the hundredths place. Here, the last digit is in the tenths place. So this is less precise. So our answer is limited to the tenths place here. So we should round this to 1.0 kilopascals. Okay, so that's our answer for part A. So for part B, it says if 6.3 milligrams of argon and 1.2 milligrams of neon are added to a 375 milliliter tube at 271 Kelvin, what is the total pressure of the gases in millimeters of mercury? So what we're going to have to do here is use the ideal gas law to convert our moles of our argon and neon into pressure. And so what we're going to need to do first is convert the masses we're given into moles. So we're going to take, sorry about that. So we're going to take our 6.3 milligrams, 6.3 milligrams of argon, and we're going to convert that to grams first so that we can use molar mass to convert to moles. So we know that milligrams, milli is 1/1000th of a gram, so 10 to the negative 3 grams. So 1 milligram of argon is equal to 10 to the negative 3 grams of argon. So milligrams of argon cancel out. So now we can multiply by the molar mass. And as before, molar mass of argon is going to be 39.95 grams of argon per 1 mole. So 1 mole of argon is on top. So the grams of argon is going to cancel out. Now we have moles of argon. So we can now calculate that out. And when we calculate out the moles of argon, we get 0.0001576. So 0.0001576. Let me double check that. 0.0001576. Okay, and that's moles of argon. And then we'll do the same for the neon. So that's going to be 1.2 milligrams of neon over 1. And again, we're going to convert that to grams. So again, 1 milligram of, not argon, neon. 1 milligram of neon on the bottom and 10 to the negative 3 grams of neon on top. So milligrams cancel out. Now we can use the molar mass of neon. And the molar mass of neon is 20.18 grams. So 20.18 grams of neon on the bottom, 1 mole of neon on top. So grams of neon is going to cancel out. Now we're going to calculate that. And when we do, we get 0.00005946. So, gosh, that's a lot of zeros. 0.00005946. 5946 moles of neon. Okay, so now we have the moles of neon. Now we can do this in a couple of different ways. One, we can use the ideal gas law to convert both of these moles separately into pressures, right? Because we have the volume. We have to convert the volume to milliliters, and we'll do that. So we have 375 milliliters of volume. We know that 1,000 milliliters is equal to 1 liter. And so now we have our volume in liters, 0.375 liters. And they also gave us the temperature in Kelvin. So given the volume, the temperature, and the moles, we can plug that into the ideal gas law equation and find the pressure. We could do that separately, once for the argon, once for the neon, and then add that together. In this case, instead, what we could do is add these two together and then use the total moles and use the equation once, use the ideal gas law equation once to find the total pressure instead of each partial pressure separately. Each way is fine. I'm going to do it with adding these together to get the total moles. That way I only need to plug it in once. Okay, so when we add these together, let me add those together. When you do, you get 0.0002170. So these added together gives you 0.0002170. And that's going to be moles total. Okay, oops. That's going to be the total moles. Total moles. And so now we can use that in our ideal gas law. So with regard to the ideal gas law, the form that we're going to use is, so we have PV equals nRT. We want to solve for pressure. So pressure is going to be equal to nRT over V. But this is total pressure. So the total pressure is going to be equal to the total number of moles multiplied by RT over V. So I'll write it down here. So here we'll have the total number of moles. So the total pressure, total pressure is going to be equal to the total number of moles that we have over here. So it's 0.0002170 moles multiplied by R. We're going to use the 0.082058 liter atmospheres over Kelvin mole. So it's going to be 0.08, sorry. It's 0.080258, and that's liter atmospheres over Kelvin mole. And then we're going to multiply that by temperature, which they gave us, which is, where's the temperature? Oh, down here. 291. So 291 Kelvin. So that's going to be multiplied by 291 Kelvin. And then all of that divided by the volume. And the volume we calculated was 0.375 liters. So 0.375 liters. So now all we need to do is calculate, but let's double check our units. Let's make sure everything cancels out. Liters cancels out with liters. Kelvin cancels out with Kelvin. And moles cancels out with moles. And so the last thing we have left is atmosphere. So we're going to calculate the number of atmospheres. And when we do, we get 0.01358. 13518, sorry. So we'll write that here. That's going to be 0.015. Let me double check. 13518. 13518, and that's in atmospheres. Okay, now notice the question here is millimeters of mercury. So now we're going to have to do one last conversion. So here we have atmospheres. So we're going to convert to millimeters of mercury. So we're going to write it, or we're going to do it up here. So, or I could do it right here. So we have, no, this is fine. So we have 0.013518 atmospheres. Oops. Yeah, maybe this is better. or I'll just here, I'll give myself some room here. I'll erase this and erase this. Give myself some room. So then we have 0.1513, 0.013, 0.013 518 atmospheres is the total pressure, and we want to change that to millimeters of mercury. So the relationship between atmospheres and millimeters of mercury is 1 atmosphere is equal to 760 millimeters of mercury. So 1 atmosphere on the bottom and 760 millimeters of mercury on top. And atmospheres cancels out. And when we calculate that out, we get 10.274. So we're going to get 10.274. Let me double check that. 274 millimeters of mercury. Now for sig figs, the least number of sig figs that we used was 2. So we have 6.3, 1.2, that's 2. Everything else is 3. And so therefore we need to limit our number to 2 sig figs. So 1, 2, cut it off there. There's a 2, so we don't round. So the final answer would be 10 millimeters of mercury. And then that, ladies and gentlemen, is how you use the Dalton's law of partial pressures to help you solve problems. I hope you enjoyed this video. If this video it helped you in any way, then please like the video, share the video with your friends, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell, and when you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you want me to help you with, please put it down below. If you have a topic you want me to cover, then write that down below as well. I would love to help you with those. Thanks for joining me and have a great day.